Welcome back to Miss Lisa's Math and Science channel. Today, right now, we're going to talk about physical science. In particular, I'm going through this book. This class is primarily for homeschoolers who want a high school math and science, but anybody who likes the way I describe things can join right on in. Like, share, subscribe. I have a goal of getting 1,000 subscribers so that I don't have to record then upload. I can make it go straight onto YouTube through YouTube Live. My kids say it's not going to happen, Mom, but I have my dreams. So this is physical science. And another thing there's several things we need to talk about before we get started. And the first of all is that as I go through what we're going to talk about today, and as long as we're doing what we're doing right now is physics. So physical science is physics and chemistry, and we're going to talk about physics first and then chemistry. And physics has a lot of math. Chemistry does too, but physics is more. And in particular, it's word problems, and it's a great way to learn how to get really good at word problems, because we love word problems and fractions, right? Maybe not, but maybe. But anyway, so what I'm going to start doing is I'm going to talk through the ideas where you can look at me. But when we get to the math, I'm going to go back and make a separate video where my camera will be on my calculator. So you can see exactly how I'm doing the math. Because instead of you having to like zoom in to see what I'm doing on the board or something like that, I think it's just easier to have two videos. So each chapter, as long as we're doing physics, we'll probably have two videos. So be sure to come back and watch the math video too. I know some of you are going, I don't like math. Come watch it anyway. You'll get to like it. The more you do math, the easier it gets. And also, we're getting to use our calculator, so that's fun, right? It's kind of like getting to play with your phone almost, but it's your calculator. And then the other thing I wanted to tell you about was, so there's two videos. That's the first one. The next one is that there are 25 chapters in this book. And what I've been doing is about a chapter a week. A normal school year has 40 weeks. So you can tell we are going way faster than a normal school year. So that's why when I do your homework, that's my other phone. I have two phones. Sorry about that. I have my YouTube phone and my not YouTube phone. And it goes back to that subscribe thing because I can't have anything on the memory of this phone or else it's too full and it won't work. But anyway, so we're going way faster. And so I do the homework that I put in the description. I don't say day 1, day 2 like I do in math. Because math, I'm releasing the videos at the right pace for them to last all year. But for the science, I'm doing a video a chapter, and there are less chapters than there are typical weeks in a school year. So I don't tell you what to do on day 1, day 2. I just tell you this is what you need to do for the chapter. You need to do these labs. You need to do these problems. You need to do this. You need to read this chapter and stuff like that. So anyway, so you could do what I'm telling you to do and do it every week when I do the video, and you're going to be through with your science for the year probably in January, maybe February. You'll be done really, really early, and then you'll be done. You will have done the whole year class. You still get credit for the whole year, but you would have finished it very quickly. Then the other thing is, or you can take longer. So just know that if you take 2 weeks for every chapter, then that's going to go longer than the 40 weeks. You're going to be doing science all summer too, because that would make it 50. That would be, that means that would take your summer too, because summer is usually about 10 weeks, and that would be too many. Unless you love it and you just want to take 2 weeks on every chapter and you want to do it all through the summer, then you can do that too. Just to let you know, think about pacing a little bit. And I guess that was mostly to the moms. So you might need to tell your mom, hey, Miss Lisa said if you're doing this as a class. All right. So what we're going to be talking, so there's going to be 2 videos per chapter though. So what we're talking today is about work. Now, in regular language, we're going to talk about work and machines and energy and efficiency and some of these. This is called Work and Machines is the name of this chapter. So in our regular language, you can think really hard about something and say, I've been working hard. I've been thinking about calculus. I've done a lot of hard work. In physics, you haven't done any work. In physics, for something to be work, you have to apply a force and it has to move a distance, because work is force times distance. So I used to show this video, and when I taught physics in public school, I used to show this video, and it had this little R2-D2 looking robot, and he would have a little broom and he'd be going work, 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 work. And it would show that he was working because he was using a force, pushing on the broom, moving something a distance, the dirt. But like in physics, I could push on this wall all day and use all my energy pushing so hard on this wall. But if I can't move the wall, I have done no work. You have to have a force and move something a distance. So just know that a lot of times in science, our common speech is not the way things are in science. And we talked about, when we talked about theory, that in science, a theory is not the same thing as just an idea, like how it is in common speech. But what makes it hard is in science, we also use it the common speech way. So it's confusing sometimes. Who knew? Science and math can be confusing sometimes. All right, so work is if you apply a force and it moves a distance. Now, when work is done, a transfer of energy always happens. Remember how last time I talked about how kinetic and potential energy can change from one to another? So say I take some books and I carry them up the stairs. Now those books have greater potential energy because of potential gravitational energy. Those books could fall and have kinetic energy and squish you if you throw them at somebody. Now, so we're going to talk about calculating work as force times distance. I'll do a problem. I'll do the problem on page 128 to show you just how a problem is done, but we'll go through that. Power. So what is power? Power it takes into account time. It's how much work is done in a certain amount of time. It could be like, it's more, think of it kind of like a rate, work per second, but it's work over time. And see, this is really confusing to us because when we think power, we think what? We think power bill. Did you get the power bill? Yeah, I got the power bill. How much money do you owe? And we don't think about power in the terms of work done in a certain amount of time. We think of it as just a way we buy electricity. You buy it in kilojoules. You pay the electric bill, the power bill. So that's another one where our common language kind of trips us up a little bit, because power is work divided by time. Now you do think of power when you see like a truck commercial, and the truck is very powerful, meaning it can do a lot of work really fast. It's a powerful truck. So there we do kind of use it more the physics way as we're talking about power. Now you'll be reading all of this in detail and looking at the examples in your book, but as we talk through it, you can get these ideas in your head. Now, what is a machine? A machine makes work makes work easier. So there are different kinds of machines. They can increase your force. They can make it where you need less force because you move something a greater distance. Remember, work is force times distance. So you can have less force and a greater distance, and you can do the work easier. For example, imagine I have a big box of books and I'm standing where there's like near a stage, and I could just jump me and the books onto the stage. Now, probably not. I'm not that agile, but maybe. Who knows? That would be very difficult. But instead, I could walk up a ramp. It would be a much greater distance, but it would be much more easy for me than trying to just leapfrog my way up onto that stage by, instead of, it wouldn't take as much force, but it'd be a greater distance. So we have to do a lot, often in physics, we do a trade. We'll trade one thing for another. We'll trade efficiency for ease and things like that. And this is one of those trades. Things get changed from one form to another. Oh, so there they've got it in the book. This person is putting a chair in a moving van and they're taking it up the ramp for it being easier. Now, we'll be doing some labs with this. So a lot of these labs, you're going to have to get your mom or your brother or somebody to help you, or get groups of students where you can do them together, because they'll just be more fun. And remember, we do labs out of the other book. We do labs out of Addison Wesley, and we do the text out of Glencoe. Glencoe's got a little bit better text, a little newer text. Addison Wesley has really good labs for homeschoolers because they use everyday materials, not so much science materials. So it's very easy to get together and do these labs. And the labs are very clearly written. So that's why I know you're like, 2 books for one class, but they're both older editions, so you should be able to get them cheap. The physical science book, you could probably find it for $8 on eBay, Amazon, the one with the labs in it, and same thing with this one. So together, they're like as expensive as one new book. I just banged the table, sorry about that. It's not an earthquake. But anyway, so they're older editions, so you should be able to get them for pretty cheap. That's one reason why I chose them. New in edition textbooks are very, very expensive, and these are just as good that are a few years old. The science hasn't changed. Nothing's changed in it, except in the one we use for lab. It's got a few things about energy that's a little out of date. Pretty much, these are just as good as a brand new book, but way, way, way cheaper. And we homeschoolers usually need to be very conscious of our money, because usually the moms have given up their job to homeschool, and so then you have to watch your money a little bit. Not everybody, but some people. All right, so different kinds. So one way of having a machine is increasing the distance so there's less force. Another one is changing the direction of force. In your book, they have an axe being used to split a log. An axe, let's see if I can make my hands, is a wedge shape. It's a kind of simple machine. And as the axe goes into the log, it is changing the direction of the force. You're hitting down on the end of the wedge, and but it causes force to go out because of the triangular shape, splitting the log apart. It's easier to use inertia, use gravity, all swinging around down on that, using really, a lot of different forces going on here to hit on that wedge with either like a mallet or an axe. And that's easier than like trying to grab a log and rip it apart with your bare hands. You can't do that, but you use that simple tool to redirect force, and it is a way of using a machine. Another one is if you say you need to pick up a heavy log, and there's a tree there with a branch. You could go over and try to pick up that log, or you could tie a rope around it, send it over the branch, and pull down on that rope, and it would be much easier than just picking it up. Why? Why is it easier to pull down than to just pick up? Because it's not like you're changing the weight or how much gravity's on it. It's because you can use your fatness. You can use your weight pulling down on that rope, and that's much easier because I can use my love handles, I can use my bones, I can use all of the fatness of me to pull down on that rope, and I'm not having to use muscle. I can use other things, other parts of my weight to pick it up. So by redirecting the force, by pulling down instead of picking up, it's much easier, and that's making the work easier because I'm using a machine. That rope going over the tree is now become a machine because it's helping me redirect force and making work easier. So interesting, isn't it? All right, now input work done by machines. There is input and output forces. So input is the energy you put into a machine. Output is what you get out. Seems simple, doesn't it? Hold on, I need water. This is video number 4 today. So then the more I talk, the more my voice starts being like, I need water. Anyway, So imagine like you want to turn a bolt. So you have a wrench and you push down on that bolt. You put a certain amount of force in, and then you get a certain amount of force out, turning onto the bolt to turn it. I can increase I can push the same amount down, but I can increase the output by having a wrench with a longer handle. And we'll talk about why in a minute. It's something called torque. But I can get a greater output by changing my machine. So different machines, you put a certain amount of energy in, and the machine can help you get more out. Now, a lot of the output of a machine is lost to, what is this our hand signal for? Friction. So whenever a machine is heating up, you are losing some of what it can do as wasted energy in friction. So a good example of that is a car. After your car's been driving around, you put your hand on the hood and it's warm, isn't it? So part of that gasoline you paid money for, instead of going for what you want it to make your car go, instead it did what you probably don't particularly care one way or the other if it does. It was instead you lost as thermal energy, and that bit of gasoline did not make your car go. Instead, it heated up your engine. So that's another thing to think about with machines, is how efficient are they. One thing we look at is their input to output and their efficiency. So in your book, you can see where they talk about input and output and energy. Now, an ideal machine, the work you get in would be the work you got out. In an ideal machine, every bit of that gasoline would be used to make that car go forward, what you want the gasoline to do. But in reality, machines aren't that efficient, and we calculate their efficiency. And I'm going to show you that in the math video that's coming next. Okay. Now the mechanical advantage is the ratio of the output to the input, and it's how much does the machine help you? You know, how much are you getting out for what you're putting in? And then we can calculate the efficiency of the machine, and that is output over input times 100, which we will look at in the math video. So you're going to have to come back and watch that to learn the math. We can increase the efficiency of a machine. How do you think we can do that? How can we get more output for our input? Remember where a lot of our efficiency is being lost is to friction. We could use oil. We could use something, WD-40. We could use something to decrease friction, and that would increase our efficiency. One of the things they do that was real big for a while in the automotive industry was to try to make cars more aerodynamic so they didn't have drag. Drag is like air friction. And they would make them real aerodynamic to try to make it where they were more efficient with gasoline. But now they've done the math, and it doesn't really help. It doesn't make any difference if you've got a boxy car, you know, or if you've got a real wedge-shaped sleek one. The amount of the air friction causes inefficiency is negligible. So you can just drive your 1978 VW bus around and don't even worry that you're driving a brick and it has no aerodynamics at all. The bus might not be efficient with the gas, but it's not because of the shape. The air isn't enough, they've discovered now. So now we're kind of getting, now that the physicists have realized that, we're getting back to some more boxy designs. You know, the Nissan Armada is very boxy. The, what is that other one? Anyway, the Kia has one. The Kia Soul is very boxy. They're not bothering with the wedge-shaped cars anymore, which is kind of nice because for a while all the cars looked alike. It was very boring. So I like it that now they're getting free to have more fun designs again. I wonder if we'll ever get them as good as like cars in the 50s or the 60s. They had some great designs then. I think our designs aren't quite as good. All right, so you have a complex machines like a car that are made of very many simple machines. So the next thing your book talks about is simple machines. And the first one they talk about are levers. L-E-V-E-R, lever. Some people say lever. In the South, we tend to say lever. I think in other parts of the world, they say lever. It's the same thing. But one time I was explaining something to someone about the different classes. And someone asked, what are you teaching in school right now? And I was like, well, in chemistry, we're learning about water pollution. And in physical science, we're learning about levers. The guy thought I said lovers, like romance. And I'm like, no, we're not learning about that. So now I always say, some people say lever, because I'm from Georgia, and I say lever, pull the lever, not the lever. And I always poll my kids that I teach now, like my tutor kids. I'll say, do y'all say lever or lever? They all say lever. So it must be a Georgia thing, because I think up north or out west, somewhere they say lever. Because there's a soap, Lever 3000 or something, and they say lever on the ads. And that was the first time I had ever heard anybody say lever. That's how Southern I am. To TV and a commercial, I was like, I've never heard that. That's funny, they say it lever. Anyway, so we're talking about levers or levers. And there are 3 different classes. The first class is where you have, okay, so there's 3 parts to this. There is the fulcrum, where it stays still, where a lever stays still. And then there is the input force that you put on the lever, and then there's where the output force goes. So the first one, the first class lever, you can think of it as a seesaw. Now a seesaw used to be in playgrounds, and it would have something in the middle and a stick, and kids would sit on each side and they would go up and down. And that was back in the 70s when I was a kid and playgrounds were not safe. Because what would happen is the bigger brother would go down and then hold the little brother up in the air, and the little brother would be like, I can't get down, Mom. And then all of a sudden the big brother would get up and go bam, and it would hurt them. So our kids would be up here and they'd just fall off and get a concussion. So now they don't have those seesaws anymore in playgrounds. But we went on vacation to the Gulf, and we went to a park, and they had huge ones where like they were for adults, and you would go up in the air 20 feet. If you were falling off this thing, you were going to break your neck. But it was so fun. It was down the Gulf in a park right on the beach. And someone said, you need to go there. It's been a couple of years, so they might have taken down those incredibly fun and unsafe seesaws. But that is your first class lever. So with this, it's anything where you push down and it pops something else up. So this would be using a screwdriver to open a can of paint. It would be anything where you push down, the fulcrum stays still in the middle, and the output force goes up. Okay, so anything like that, a crowbar, a carpenter's friend, anything like that, the back of a hammer, where you are pulling up a nail because you're pushing down, the nail goes up. The second class lever is, you can think of like a wheelbarrow. So the fulcrum is like the tire that stays still. You pick up and the stuff picks up. So these things go together, and it makes less force. It's easier to pick something up with a wheelbarrow than it is to just pick it up, because I can carry a bunch of firewood in a wheelbarrow and I can't carry that much in my arms. So it is helping, and the reason why it helps is because of torque, that word that I told you I'll tell you about in a little bit. But it's whenever you have a force and a lever arm or a lever arm, the longer the arm is, the less force you need to make your output force. It's a rotational force called torque. So My dad used to say, that torques my jaw, and I didn't know what that meant. It was a country expression, and it means it's like being hit in the face and turning your jaw. Anytime you have a turning force, it's torque, and the longer the lever arm is, the less force that's needed. So we use those kind of machines all the time. Any handle, anything that's rotational, is how you open doors. The doorknob is on the edge of the door. They're not in the middle. I know that's how it is in The Hobbit, in Middle Earth, but in real life, where there's real physicists and not artists making the door, the doorknob's always going to be on the edge. It makes it easier to open the door. If the doorknob's in the middle, it would be much harder. If you put the doorknob all the way over where the hinges are, it would be very hard to open, because the secret of this machine is having a long lever arm, and or lever arm if you're not from around here. So it's your torque is your force times the length of the lever arm, and you can have less force if you have a longer lever arm. So I have a little story to tell about that. One time my brother was needing to get bolts off of a car, and they were like stuck. So he knew about torque. So instead of, he didn't have enough force to turn it, so he got this extender on it that he put on his wrench, because the longer you can make it, the less force you need. So he got this really long torque extender to the wrench, and he put on, and he turned it, and he had mechanical failure. Instead of the bolt coming off, the whole screw just twisted and mangled the metal, and then it was even a bigger problem than he had before, because now he was going to have to like drill out the whole thing. So, and it was metal. How do you drill metal? That was a big problem. Okay, so the third class of lever I think of is a broom or a rake. Your book has a baseball bat. But with the third class lever, there is no mechanical advantage. So all it's doing is extending your reach. So an example of that is if you're raking, so you've got the part that's still when you're raking leaves. We'll do raking leaves. Where it's still is where your hand is. And where the final force is where the leaves are being raked. It is much easier to use a rake than to get down on your hands and knees and pick up all the leaves. So what that third class lever does is it extends your reach and makes your reach further. So like, and instead of having your hand that's only this big, you can have a great big rake and do a bunch of the leaves at once. It's the same thing with sweeping the floor. It doesn't really give you a mechanical advantage, but it's much more convenient to use a broom than to get down on your hands and knees and try to get the dirt off the floor. And then they use a baseball bat. It's extending the reach of the baseball player. Now, another kind of thing we use is a pulley. And pulleys, the first kind of pulley is where the rope goes up and then down. And this is the rope over the tree I was telling you about. All it does is change the direction of the force. It doesn't give you a mechanical advantage, but it makes work easier because you can use your fatness to pull down, and it's easier to pull down for us than it is to pick up. Then if you add pulleys to it, it is called a block and tackle, and the more pulleys you add, the further you pull the rope. So just like the ramp, how you had to go a greater distance but it gave you much less force, pulleys are the same thing. The more pulleys you add, the longer you pull the rope to move it, but it takes much less force. And you can add pulleys and pulleys and pulleys, and they have it where it's bunches of pulleys, and that's when it's really normally called block and tackle. But even skinny, not very strong me, it can and has picked up a big engine, 500 pounds, using a block and tackle. And a lot of times when you see these in a mechanic shop, it's a chain that you're pulling. And I've done it. I've picked up an engine before using a block and tackle going. You have to do it a long time on that chain, and then it just moves a little bit. But you can move this very heavy thing They use them in ships. You see all these, in loading things, you'll see where they use a system of pulleys, and it really increases your mechanical advantage. Another one is a wheel and axle. So you can think of it as a steering wheel on a car. That it is redirecting force, but it's using the torque force. The bigger the wheel is, the less force it takes to turn the axle, and that, so you can get mechanical advantage that way. But think of it as a steering wheel, anything like that. Another one is the incline plane. That was the first one I told you about, the ramp. Well, the first one I told you about was the wedge. So the ramp, like a handicap ramp, that you do a longer distance, but that it takes less force. Now, the one that's really interesting is a screw. Let's see if I can do it with this piece of paper right here. Let me get a piece of paper, not the one I wrote on of the videos I need to make. Okay, here's a piece of, oh, I can do it with this. Here's a Post-it note. This'll work. Okay, I'll use this. All right, so if you were here in class, I would get you to get a triangular shaped piece of paper. And then I would have you make a mark down the side so that you could see the edge. So I'll do this for you. Whoop. It's more fun with sound effects. Okay, and then if you take your piece of paper and wrap it around, you can see I had an incline plane. I wrapped it around this, and now I have something that looks like, and could be, if it had a little triangle on it right here, it would be a screw. So a screw is a type of incline plane just wrapped around something shaped like this, a cylinder. So you can see in your book a picture of that. So anything like they've got peanut butter or a wood screw, all of that is using an inclined plane wrapped around a cylinder. A wedge is two inclined planes joined together. So you've got one inclined plane and then another one. So you imagine another one out here. And then that's a wedge, and it works by redirecting force. Compound machines is where you take simple machines and put them together. A bicycle is a good compound machine. And I think that's it for our chapter. Yes, it is. So you're going to read the chapter, you're going to do the labs, and you're going to come back and watch the math videos so that you can get good at the math. All right? So like, share, subscribe to Miss Lisa. Science is great. Come back and see the math, because math is great too.